Hello everyone, my dear friends. How are you all? This is Ayujan and I welcome you all to Educata Accomplished Learning. Okay guys, so this is the first lecture of our subject which is named as heat transfer, in which we are just going to deal with the introduction. Okay, so what do we mean by heat? The first question that comes into our mind is, what do we mean by heat? What is heat? See, heat is basically a form of energy. Okay, what is heat? It is basically a form of energy. What form of energy? It is basically a form of internal energy. Yes, can we say it is form of internal energy? Yes, internal energy is what? Internal energy can be vibratory energy. Okay, vibratory energy. Internal energy can be molecular energy. Internal energy can be heat energy. Okay, it is basically a form of internal energy. Okay, now suppose that we are talking about heat transfer. Okay, suppose that we are talking about heat transfer. What do we mean by heat transfer? Heat transfer is basically the transfer of heat. Can we say that? Can we say that heat transfer is basically the transfer of heat? No, we can't say that, because heat transfer is a transfer of heat per unit time. Okay, it is a transfer of heat per unit time. But why will this heat transfer take place, Ayush? Okay, why will this heat transfer take place? Suppose that see, we know that the unit of heat is what? Unit of heat is heat is what? No, it is unit of heat is joules. Yes, but if we say that unit of thermal conductivity or unit of heat transfer, it is basically we are going to deal with what? Yes, we are going to deal with what? Clear? So suppose that this is a this is a slab, this is a solid slab, or you can say that this is a slab basically. Now what is happening over here? Here the temperature that we are having is basically greater, means it you can consider the temperature as 120 degree. The temperature over here is 120 degree, and the temperature on the other side, the temperature on the inward side is 120 degree, and temperature on the outward side is 50 degree. What will happen now? What will happen because of this temperature difference? See, we will have to maintain an equilibrium over here. Okay, we will try to maintain equilibrium over here. What will happen? See, the temperature, this 120 degree will go on decreasing, and this 50 degree will go on increasing till we come to the temperature in the mid, which you can consider as any, maybe 85 degree or 70 degree or 50 or 90 degree, maybe any. Okay, but when both these temperatures become equal, okay, see, when it will suppose it will come from 120 to 75, and this will also come from 50 to 75, then we say that a thermal equilibrium is being maintained. Okay, this point is clear to you. But another question is that why we are reading about heat transfer, why we are studying about heat transfer, when we dealt with heat in thermodynamics also. We dealt with zeroth of thermodynamics, we dealt with first of thermodynamics, we dealt with the second of thermodynamics, we dealt with exergy, we dealt with entropy, we dealt with heat in various forms in thermodynamics. Then why are we dealing with it in heat transfer? This is the basic question. Okay, so basically, what is the difference in thermodynamics and heat transfer? The difference is pretty simple. In thermodynamics, we are going to deal with three types of equilibrium. What are they? They are chemical equilibrium, they are mechanical equilibrium, they are thermal equilibrium. We are going to maintain these three equilibriums. What is an equilibrium? Equilibrium is basically the condition of rest. Okay, suppose the condition when there is no heat transfer taking place, or yes, you can consider it as a condition of rest. Okay, that is the equilibrium. Now, okay, so in thermodynamics we are dealing with three equilibriums, but in the case of heat transfer, what we are dealing with, we are dealing only and only with thermal equilibrium. Okay, we are dealing only and only with thermal equilibrium. Okay, in the case of heat transfer, in thermodynamics, what we are dealing with, we are dealing with the quantity of heat. We are dealing with the quantity. Okay, means we just want to know that this much heat is produced. We don't want to know in how much amount of time it is produced. Okay, we just want to know that this much heat is produced. Like if we say that 20 joule of energy is produced, or 20 joule of heat is produced, or 20 kilojoule of heat is produced. Okay, so this is basically a quantity. Okay, in thermodynamics, we are basically dealing only with the quantity of heat being produced. But in the case of heat transfer, we are dealing with the rate of heat being produced. Now, there are various modes of heat transfer. Okay, heat is being transferred in various modes. The modes that we are going to deal with, there are basically three modes of heat transfer. Okay, the first mode that we can say is conduction, second mode is convection, and the third mode is radiation. So in this particular subject, we are going to deal in detail with all the three modes of heat transfer. There are three modes of heat transfer, and we are going to deal in detail with all the three modes of heat transfer. See, in the basic concepts, I am just giving the basic discussion on what all these are. Okay, this is not a detailed discussion. This is just a basic discussion of what all these modes are. Okay, so first dealing with the first mode of heat transfer, which is the conduction. What is conduction? Conduction is that mode of heat transfer in which the temperature gradient in a stationary medium, okay, when the heat is transferred in a stationary medium, suppose that this is a solid body, okay, this is a solid body, okay, and the temperature over here is going to consider as 120 degree, 120 degree over here, and suppose 50 degree over here. What will happen? They will try to maintain equilibrium, and for maintaining the equilibrium, what will happen? The heat will flow from higher temperature to lower temperature. Is it possible that the heat flows from low temperature to high temperature? No. According to Clausius' statement that we have studied in thermodynamics, it is not at all possible that the heat is flowing from lower temperature to higher temperature without any external work being done. Okay, means some external work is to be done. We want that the heat, if we want the heat to flow from lower temperature to a higher temperature. Okay, is this point clear to you? So heat is always flowing from a higher temperature to a lower temperature. Keep this thing in mind. Now heat conduction can occur in solids as well as fluids. Okay, conduction can take place in solids as well as fluid. Okay, but first let us clear some concept about what a fluid is. Any substance which generally flow is known as a fluid. Okay, is it always so? Can we say that any substance which is flowing is always a fluid? No, this statement is incorrect. Why this statement is incorrect? Because suppose that this is a glass, okay, this is a glass. Okay, now suppose this glass was something like this 100 years ago. Okay, this glass was something like this 100 years ago. Now after 100 years, if we see this particular glass, if we are looking towards this glass after 100 years, what will we see? We will see that this glass became something like this. Okay, some of the mass of the glass started flowing in the downward direction, and why, and this is also flowing. So can I say that this glass is a fluid? No, I can't say, because fluid does not only mean that any substance that can flow. Fluid basically means that there should be a continuous deformation if a shear force is applied. Okay, suppose this is a fluid element, and we are applying a shear force from somewhere over here. What will happen? This fluid element will move something like this. After that, what will happen? This will move something like this. After that, what will happen? It will move something like this. Means there is continuous deformation taking place in the case of fluids. Okay, so whenever there is a continuous deformation, we call that particular body as a fluid. After this, we are going to study about, see that this conduction is taking place in both solids as well as fluid, but in both the cases, there is a different way the conduction is taking place. Okay, there is a different way in which the conduction is taking place. In the case of solids, if we just look towards the structure of solid, it is somewhat like this. Okay, it is a closed packed structure. Okay, somewhat like this. This structure is closed packed, such that the molecules inside a solid can't move from one place to another. Okay, the molecules inside a solid can't move from one place to another. Okay, so because the molecules can't move, the conduction will take place in the by flow of free electron. See, suppose you are having any metal piece or non-metal piece, but in the case of non-metals, this condition will not take place. But if we just consider metal piece, suppose you are having copper. Okay, you are providing energy to this copper. What will happen? Copper will convert to Cu2 plus. Okay, this copper will convert to Cu2 plus, and then after that, what will happen? This two electrons will be removed. Okay, two electrons will be removed, and these two electrons will just flow from one place to another. Okay, these two electrons will just flow from one place to another, and they are thus helping in the flow of heat. Okay, they are thus helping in heat transfer. Okay, so first method in case of solid is basically by the flow of free electrons, but this majorly takes place in what? In metals. Okay, this majorly take place in case of metals. In case of non-metals, what will happen? Suppose that you are having chlorine. Okay, suppose that you are having chlorine. In the outermost shell of chlorine, how many electrons are present? In the outermost shell of chlorine, 7 electrons are present. 1, 2, 3, 4, 5, 6, 7. 7 electrons are present. So can you provide so much energy that this electron will get removed? No, it is not possible. Okay, we are not going to provide this much energy so as to remove an electron. Either what we will do, we will just supply an electron to it so that its octet gets completed. Okay, so flow of free electrons, this takes place basically in the case of what? In the case of metals. Okay, another method is basically what? It is lattice vibrations. What is lattice vibration? See, when we are just providing energy somewhere, okay, when we are just providing certain amount of energy to it, what will happen? These electrons will just vibrate. Okay, sorry, these atoms will just vibrate at their positions. Okay, these atoms are just vibrating at their position, and because of their vibrations, the energy is going to be transferred. Okay, the energy is going to be transferred. See, this is a homogeneous arrangement. In the case of solid, it is a homogeneous arrangement. You can say that because everything is standing in sequence, something like this. Okay, everything is there in sequence, something like this. Suppose that you just break this particular piece, then this will also break, this will also break, this will also break, this will also break, this will also break. Okay, suppose there is a chain of a cycle. Okay, this is a chain of a cycle. You just throw it, what will happen? The second one will also get down, third one will also get down, fourth one will also get down, and something like this what happens. Okay, so in case of solids, what is taking place? Lattice vibration, the conduction due to lattice vibration is taking place. In the case of liquids and gases, what is happening? See, the spaces between the molecules of gas and liquids, the spaces between the particles of gas and liquids are very much huge. Okay, and because of those huge spaces, what is happening here? Here the conduction is taking place due to collision of molecules, and that too because of the random motion of molecules. What will happen? See, we have just applied energy, certain amount of energy to this molecule. Okay, we have just applied certain amount of energy to this molecule. What will happen? What is happening? Yes, what will happen? It will just move over here and supply that energy to this part. It will just move over here, supply this energy. It will just move over here, and then the supply of energy is taking place something like this in case of liquids as well as in the case of gases. Okay, so this is the method in which the heat conduction is taking place in the case of solids, liquids as well as gases. Okay, is this point clear to you? Now we are going to learn about a major law in the case of heat conduction, that is known as Fourier's law of heat conduction. Okay, this is known as what? This is known as Fourier's law of heat conduction. Now, what does the Fourier's law of heat conduction say? Tell us. The Fourier's law of heat conduction tells us that the rate of heat flow per meter, the rate of heat flow is basically directly proportional to what? Directly proportional to the temperature gradient. Okay, it is directly proportional to the temperature gradient. This is the statement of the Fourier's law of heat conduction. Q dot x is the rate of heat flow per meter square. K is the thermal conductivity, and negative sign. Why is this negative sign over here? Q dot x is equal to minus of kx dt by dx. See, suppose that the heat transfer is taking place. Suppose that the heat transfer is taking place somewhere over here. Suppose this is a body, and this is a high temperature T1, and this is a lower temperature T2. T1, and then here is T2. Heat transfer is taking place from T1 temperature to T2 temperature. Okay, means T1 temperature is greater than T2 temperature. Can I say this? Yes, T1 temperature is greater than T2 temperature. Now, in this case, dt is basically representing what? Dt is representing the second temperature minus first temperature, means T2 minus T1. Okay, this dt represents T2 minus T1. See, if we are saying that T1 is greater than T2, and what we are doing? We are going T1, we are doing T2 minus T1, then will this value be a negative value? Will this value be a negative value? Yes, it will be a negative value. Okay, so this value will become negative, but we say that the rate of heat flow is always positive. That's why we just assign this minus sign over here. Okay, is this point also clear to you? Now suppose that here this temperature was a function of x only. Okay, means it is a function is the heat conduction is taking place in x direction only. Suppose that we are taking the temperature as a function of x, y as well as z, means all the three coordinates. Okay, if we are just taking it as a function of all the three coordinates, then what can we write? We can simply write that q is equals to minus of k into gradient of temperature, into temperature gradient. Okay, can we write it? Yes. But what is this temperature gradient? Temperature gradient is the partial differential of temperature, uh, uh, a partial differential of temperature with respect to x, partial differential of temperature with respect to y, and partial differential of temperature with respect to z. The summation of all these is known as the temperature gradient. Means we just have to differentiate them partially. Okay. Now, how is this k helpful to us? Okay, k is basically the thermal conductivity. The higher the thermal conductivity of a material, the higher the rate of heat flow. Okay, the higher the thermal conductivity of a material, the higher the rate of heat flow. This is the basic thing. And the value of k depends on material to material. Like the value of thermal conductivity is different for aluminum, it is different for copper, it is different for zinc, it is different for silver, it is different for aurum, for, you can say, Ag. Okay, for all these materials the value of thermal conductivity is different, and that's why we can say that the rate of heat transfer is changing when we change the material properties. Okay, is this point clear to you? Now we will continue after this from the next lecture. Okay, till then, see ya, take care, and bye bye.